Okay, so first of all, I've handed you this paper, should be coming back to you if you're in the back of the room. I have in the past done extra credit for what I call a science notebook, which is just including some things that are like extra notes together. But in the past, when I had people turning it in at the end of the semester, either they weren't completing it and not getting the extra credit, so they ended up turning in work that they didn't get credit for, which I don't want, or they weren't doing it when it would help them, which would be before a test or a quiz. So what I'm going to do is I'm going to have 3 times that you can turn this in. So I mentioned to you I took away my example. The atoms sheet, where you had the foldable. That is one of those items. There will be several of these you can choose from. You can have up to 5 of them. They need to be together, like in a folder or in, you can tape them into a notebook, something that makes it easy to keep them together, not just separate sheets flying around. You need to make sure your name is on it so I don't have to try and figure out who gave it to me. And I want it to be easy for me to evaluate. I'm not trying to create more work for myself. So we want them together by topic. So if there are a couple of things on significant figures, keep those things together. Like I said, put your name not just on the folder, but on like every paper so that if something comes out, they are together. And then there are sometimes when you'll have like a smaller piece of paper that maybe is a slider or, goes on like the foldable X thing, went on the corner. Make sure you attach those. Don't just like randomly shove things into the folder. Okay. So in chemistry, when we are working in the lab, we're generally working with grams of materials. We're not working with milligrams or nanograms. In order to actually, put it somewhere, it has to be in grams. We don't usually have kilograms worth of stuff. So that's kind of the range that we are in when we are dealing with materials. Now, sometimes in industry, you would be doing kilograms, but for lab, it's usually in grams. If I were to count the number of atoms in there, that would probably be somewhere in the ballpark of 10 to the 22 to 10 to the 24 atoms. So you might remember from when you first started learning about exponents, that when you do tens, this kind of corresponds to how many zeros you have. So if we think about how many people are on this planet, there's roughly 9 billion people on the planet. So that's 9 times 10 to the 9th. So that number looks like this. $9 billion. Okay, and that's a really big number to have to be working with. But if I had 10 to the 22, that would be this. That's incomprehensibly large. That is so big that we really just can't wrap our minds around. So we never really count the atoms that we are working with in lab. We need something smaller to deal with. So we have the number of mole, which is a way of saying this large group here, that is 1 mole. And I will just think of those at one at a time. Kind of like if you go to the store, you don't say, I'm going to go and buy 3 eggs, or I'm going to go and buy 15 eggs. You buy them by the dozen. You either buy 1 dozen or 2 dozen. Sometimes you can buy a dozen and a half. So this is a way of breaking down this number into something smaller that we can wrap our brains around. So a mole is equal to 6.02 times 10 to the 23rd. So in October, on the 23rd, we call this mole day, 10/23. So you'll hear more about that in October. We don't really need that number for anything, but we just have this number as a way of saying a whole mess of. So when I have 1 mole, I have a whole mess of those things. If I have 3 moles, I have 3 whole messes of those things, okay? But it is also our way of quantifying and comparing things. So if I have 1 whole mess of hydrogen and 3 whole messes of carbon, I can say I have 3 times as much carbon as I have of hydrogen. So we need that ratio there to help keep us on track. So how does this relate to something we can do in lab? On the periodic table, PT is periodic table. On the periodic table, the atomic mass equal to the mass of exactly one mole of atoms of the element. And we know that for many elements, each individual atom may not weigh the same as other individual atoms. So the mass that's on the periodic table is what we call a weighted average. We take the number of atoms in a particular or in a typical sample of, let's say, oxygen that are oxygen 16, and the number of atoms in a typical sample that are oxygen 18, and we give more weight to the oxygen 16 because almost all of them are going to be oxygen 16, and give very little weight to the oxygen 18. And so we do that average comparing percentage wise. 99% this, 1% that, and we combine those. So the weights on the periodic table aren't the weights of any given atom unless it's something like fluorine, where there's only 1 natural isotope. So there are a handful that it's like that, but for the most part, it's a weighted average. Which works fine because we're dealing with natural samples anyway, and we have so many atoms that it all averages out. We're not going to have too small of a sample size. So what this means is that if I have 12.01 grams of carbon, I have 1 mole of carbon. That makes sense? Check out the periodic table, 12.01, that's 1. And if I had 24.02 grams of carbon, that would mean I'd have 2 moles of carbon. Okay. In our lab, what we want to do is figure out what is the ratio of moles of water to moles of, you're doing magnesium sulfate, I think. So we need to figure out how to find the molar mass of a compound. And you will not be surprised to find that you're just going to add up the masses of the atoms. So for each element, I'm going to have to look at the periodic table, and I'm going to say, okay, hydrogen is 1.01. And then whatever number follows it, that's how many of that element I have. So I'm going to have to multiply this by 2. Okay, so I have 1.01 times 2, and then I have an oxygen, and that's 16.00. Now your periodic table may say 15.999, but if I round that to 4 digits instead of 5, it's the same thing as 16.00. Okay, so for most of the elements before calcium, which are most of the elements that you work with, the number is somewhere close to a whole number. Magnesium is not, so when you calculate for magnesium sulfate, it'll be a little bit off, but most of the time it's pretty close to a whole number. I only have 1 of those, so I'm only going to count it once. And so this is going to be 18.02, and our units are grams per mole, which is saying 1 mole of this will have this mass in grams. Okay. So that would be how I would find the molar mass. What if I wanted to know how many moles I have? Moles will be equal to the mass divided by the molar mass. So I know if I have 18 grams of water, I would have 1 mole. Well, what if I had 100 grams of water? So 100 grams divided by 18.02. Something like 5.6. 5.55. Okay, this bottom number was grams per mole, top number was grams. Cancel the grams, and my units left over are moles. Okay. Now, let's say I had done the same kind of math on my magnesium sulfate, and I had come up with, well, this isn't the number for magnesium sulfate, so I don't want to throw you off. So I'm going to say my random ionic compound ZX, I had 1.11 moles of that. I did the same kind of math for ZX. I looked it up, blah, blah, blah. And I only have 1.1 moles. I want to know how many waters I have for every ZX compound because I want to know how many waters of hydration there are. So what am I going to do? I'm going to divide. And usually we're going to divide the bigger number by the smaller number. That's most likely going to give us a whole number. If I do it the other way, I'm definitely not going to get a whole number. So I'm going to say I have 5.55 moles of water to 1.11 moles of random compound ZX. And that's going to give me 5. Okay. Works out to a nice whole number. Now, probably when you do this in lab, it's not going to be 5. It might be 4.89. It might be 5.12. So you're going to say, okay, what whole number is it closest to? Okay. This is the only time when we're trying to figure out how many waters of hydration there are, or trying to figure out an empirical formula. That's the only time we say, that's close enough. Let's just round it to a whole number. Most of the time we care about sigmas, but in this case, we're going to round to the whole number. So we would say the compound is ZX 5H2O, which would be whatever this compound name is. That's not a real compound. Pentahydrate, right? Okay. Questions about the quiz before I hand out? Oh. Not at this point, no, because we want to have the mole ratio for their exact numbers. Now I can round the ratio, so I round ratios, I don't round moles. Sometimes you might end up in lab, you'll end up with a really small number. So you might have 0.0412. We're not going to round that. We're going to compare that to, you know, whatever your other number is, 0.206. Okay, neither one of those is really close to a whole number, but when I do the ratio is close to a whole number. So we only round the whole number, only round the ratio up. Yes. Yes.
This is pretty relevant to the quiz, but I was searching about molecular weights. So it's like, let's say, cadmium is like 112.41. Do I round it up to?
Use 2 numbers after the decimal point. I will always.
So it's like usual rounding. Okay. I sometimes have a feeling that.
In reality, when you're doing the heavier elements, if you only use the whole numbers, you'd probably be okay. But we don't want to drop significant figures if we don't have to. And if I have a hydrogen in there, since I only have one number before this, the decimal point, I need those numbers after the decimal point.
Okay,
so
we need those numbers.
Alrighty. This.